Hi, and welcome back to another episode of Che 101. Today, our subject is on Che, aka Analytical Chemistry for Engineers. This is the subject you're expected to take in your first year, second term here in DLSU. And our topic would be on indirect titration. However, before we start, of course, I'd have to introduce myself. So my name is Eliza Tan. I'm taking DSMS Chemical Engineering currently, and my email address can be seen in the screen in case you want to email me for any concern or whatsoever. Our outline is as follows. We'll start with the problem statement, and then we'll discuss the theories that you need to be equipped to solve the problem, aka indirect titration and the digital method. Afterwards, we'll attempt to solve the solution, and then we'll end with a summary of everything you need to know again to solve problems related to indirect titration, as well as tips that I have for you to solve indirect titration problems more efficiently. So to start things off, we have our problem statement, which I will read. So in this case, we have a 0.6430 gram sample of water-soluble fertilizer, which was dissolved and analyzed for nitrogen using the digital method. After digestion, the distilled ammonia was collected in 100 ml of 0.334 molar boric acid, and this solution required 21.40 milliliters of 0.2020 molar hydrochloric acid for titration to the metal red endpoint. Our goal in this case is to calculate the percent nitrogen in the fertilizer, and we are given two reactions. I will be explaining the reactions later on because we'd first have to understand what indirect titration is. I'll first give a short recap on what titration is because I'm not sure if at this juncture you've already discussed direct titration, which should be the case, but just to catch everyone up. So let's say you have a solution of unknown substance and you call that your analyte, and you want to know the concentration of that particular substance in your solution. So, how do you do that? Well, you can react it with a substance of known concentration, which you call your titrant, and that is the substance you put in your burette, which you will be using a lot in the lab counterpart of this Che. And so what happens? You react your titrant with your analyte until a point where the amount of moles of titrant you add up causes all your analyte to be consumed. So what do I mean by this? So let's say, for example, your analyte is acetic acid. So that's CH3COOH. And your titrant is NaOH. Your goal is to determine the amount of acetic acid in your solution. And you know the concentration of your sodium hydroxide. Looking at the reaction tells you that they are stoichiometrically related. I'll be adding in the results for your reference, but the gist is they are in 1:1 ratio, meaning 1 mole of acetic acid will react with 1 mole of sodium hydroxide. And since you know the amount of sodium hydroxide that you added such that all your acetic acid is consumed, which you call the equivalence point, you can use that to determine the amount of acetic acid in your analyte. And from there, you can determine the concentration of your unknown solution in terms of acetic acid. So that's the gist of titration. But sometimes, there are scenarios where you cannot directly react your titrant with your analyte for many reasons. So, one example, let's say you want to determine the concentration of your unknown solution with this particular analyte. But you don't have with you the titrant you need to react with that particular analyte. But you have another reagent that you can use, react with something else to give you that titrant you need. And so what you do, you'd first chemically react the reagent you have to get the titrant you need. And that product, that particular product, the titrant, is what you use to analyze or determine the concentration, the amount of your analyte in that solution. So that's the gist of indirect titration. Another particular instance why you might need indirect titration, like, of course, there are times when you'd ask, why can't I just directly react your analyte and titrant? Another possible example is when your analyte is in a form originally that cannot react with your titrant. So what do I mean by this? Because usually your analyte is either in solid form or liquid form. Liquid form is easy because you can just directly react it with your titrant. Solid, you can just dissolve it in, let's say, water. But what if your analyte is in gas form? It can't directly react with your titrant. And so you'd have to make your gaseous analyte into a liquid form, that would react with your titrant. Let's say you trap it in a liquid. And that is the point of indirect titration. So to give it a more formal definition, indirect titration is the technique where you don't directly titrate the substance of interest, but you titrate it rather with something, you react it with something else first, and then that product you get is what you titrate with your substance of interest. This particular reaction is an example. We won't be solving a problem with this reaction as of this moment, but to explain it briefly, this is a scenario where, for example, you want to determine the molarity of your hydrochloric acid, but you don't have hydroxide ions with you, but you do have mercury oxide. You can't react mercury oxide with hydrochloric acid, but you can use hydrochloric acid, combine it with iodine ions and water to form your hydroxide ions, which you can use to react with your hydrochloric acid. And from there, you can determine the amount of hydrochloric acid in your solution of unknown concentration. And then your unknown concentration or solution of unknown concentration will become a solution of known concentration. And that's what you call indirect titration. Moving on, we have another scenario, but this can be explained using the Jidal method. So this Jidal method, it's basically indirect titration, but it's a special kind because it's more focused on determining the amount of nitrogen in a substance. And of course comes the question, what's up with nitrogen? If you're not interested in understanding this part, you may skip directly to the solution part because, well, this is just for you to understand the problem better. But if you know the indirect titration and how it works, you can skip straight to the solution part. But for those who want to understand the Jidal method, this is very useful because in many industries, you need to determine the amount of nitrogen to determine other substance. Like, let's say for example, in the food industry, nitrogen can be associated with protein. And in a lot of food related stuff, you need to know the amount of protein because it's important for labeling. And from there, that's why the Jidal method was created to determine the amount of nitrogen in a more effective way. Another scenario where the Jidal method can be used is in analyzing fertilizer. But it's also applied in many other instances. In short though, the Jidal method is a 3-step process that measures the amount of nitrogen in a substance. And this 3-step process is, of course, composed of 3 steps, namely digestion, distillation, and titration. To explain this, we first have to understand that nitrogen is usually found in an organic substance, and meaning it's hard to titrate it directly because it's possible that that nitrogen is strongly covalently bonded in the organic molecule and may not react with your titrant, which defeats the purpose of titration since you want to know the amount of nitrogen in your substance. And this is where digestion comes in. So it breaks down that substance using heat and particular enzymes so that it's easier to release the nitrogen. And this nitrogen is distilled, namely, it's separated through distillation by evaporating it or turning it into gas. And this gas, usually in the form of ammonia, is trapped with a liquid. And this liquid is what you use to titrate with your substance of known concentration or your titrant. And that is the gist of the digital method, which brings us back to our problem. And now we're back to our problem. So let's read this problem again so that we'd further internalize what we're trying to solve. And while I read, I'll be highlighting some numbers that we may need in order to solve the problem. May or may not need. Because it's easy to get overwhelmed with the amount of numbers that you see in this particular problem. Again, this applies the digital method. And I'll be solving this handwritten so that you can solve alongside me and see if our solutions compare accurately with each other. To start, we have a 0.6430 gram of sample of a water-soluble fertilizer that was dissolved and analyzed for nitrogen using the digital method. After digestion, the distilled ammonia was collected in 100 ml of 0.334 molar boric acid, and this solution required 21.40 ml of 0.2020 molar HCl for titration to the methyl red endpoint. Calculate the %N in the fertilizer. So, what I usually do as I start solving is to determine the required of this problem because it will give you an indication or an idea of what you're trying to solve for. And in this case, it's the % nitrogen in the sample. So moving forward, we can start from what I'm seeing. We have two important values. Well, we have the 100 ml of 0.334 boric acid, but in order to understand why I didn't underline that, we'd have to understand reactions. So we have two reactions: the preliminary reaction and the titration reaction. So we can see that from the fertilizer, we get NH3, ammonia, and it is trapped in boric acid. So this is your 100 ml of 0.334 molar boric acid. And from what I'm seeing, we won't need that because we can instead use the values we get from here to determine the amount of this, and from here you can stoichiometrically get the amount of NH3. But going back from the problem, we can see that from NH3 we can get ammonium ions and H2BO3. And comparing the two reactions, one thing that's common is the presence of this particular ion. Because this ion is what is used to combine with HCl to determine the amount of NH3. And when you reach equivalence point, because you already know the amount of HCl or hydrogen ions you reacted, which reacted with your H2BO3, you can determine your H2BO3. So how would I solve this problem? Well, we'll start off with your HCl. So that's 21. Oh, let's put this rather under so we can make it a one big space. So 21.40 ml of 0.2020 molar HCl. So you can write this as millimoles per ml because that's still the same reaction. And from that, you can determine the amount of HCl you reacted with H2BO3 when you reach the endpoint. So, stoichiometrically, assuming everything's balanced, well, you'd have to check first if this is balanced, but I know this is balanced. You know that 1 millimole of H2BO3, or rather 1 millimole of HCl, which reacts with 1 millimole of H2BO3. So this is HCl. So why did I make it in this method? Because you know that eventually this HCl will cancel out. So that is what I use as my basis. And then multiplying that from there, you know this, which is an important an important aspect to know, because you can stoichiometrically determine this, which will tell you the amount of nitrogen in the fertilizer. So going back, 1 millimole of H2BO3 is stoichiometrically related to 1 millimole of NH3 ammonia, meaning for every millimole of ammonia, you get 1 millimole of H2BO3. And there, you can know the amount of NH3 in your solution. But since we're looking for nitrogen only, we can just say that 1 millimole of NH3 is equal to 1 millimole of nitrogen, right? And then from there, you can get the grams of N in that sample. So 1 millimole of N is equal to approximately 4.01 milligram of N. And if you double check your stoic relationships, you'd see that they all eventually cancel out, leaving you with the amount of mg, the milligrams of nitrogen in your solution. Okay, so solving that, let me get my calculator. And you can compute with me if ever you have your calculator with you. We should get 60.06 milligram of nitrogen. But since we're given the values in gram, we'd have to convert it into grams, because, well, we're looking for percent nitrogen. So percent nitrogen is equal to 60.06 milligram of nitrogen times, we convert this to gram. Normally you can just do this directly, but 1 milligram is equal to 10 raised to neg 3. Oh, sorry. Oh no. Turned. Is equal. 1 milligram is equal to 10 negative gram. And that is equal, and over the total amount of samples of 0.6430 gram sample, and then times 100, since we're looking for percentage, that should give you, apologies, this is 60.56. Well, it's normal, so it's important to double check your calculations from time to time to see if you're right. And you get I got 9.42% nitrogen. So this is the amount of nitrogen in your fertilizer. Well, following sig fig, you're given 4 sig fig. This is important. So following sig fig, 9.419% nitrogen. Here we go. And now we're back in our PowerPoint. So to summarize what we have learned today, I have prepared these 3 points. So number 1, indirect titration. You don't directly react the analyte with the titrant. Number 2, the Chital method is a useful method in analyzing the amount of nitrogen in a substance. Very useful for the food industry and whatnot. And lastly, when solving the problem, understand what it is looking for and always have a checkpoint so you don't get careless like me earlier, and so you don't do the same thing, make the same mistake in your exams. So my tips, it's really understand what the problem is looking for, because usually the problems you're given are very long and you might be confused in the end on what you're trying to look for in the first place. So highlight what your required is, and then use that as your basis for your solution. And then always have a checkpoint to make sure that you're inputting the right things and your answers still make sense. So that's it for today's video. For any questions, feel free to contact my email at the start of this video, or the chen.acads email, which is seen on the screen. And we also have a Facebook page called Academics Hub, which I highly suggest you follow, because there are a lot of exciting activities that the academics committee of Chen offers. And by extension, please do follow the Chen FB page for more info on Chen, and so that you can join our activities from time to time. Once again, I'm Eliza Tan, and thank you for listening.